Hello my dear students, welcome back to NEET 1. So this is our session 4 on haloalkanes and haloarenes chapter, right? So in the last class we have discussed the preparation methods of haloalkanes and also haloarenes, right? So in this session we will be discussing about their chemical properties. What we are discussing? Chemical properties of haloalkanes and haloarenes we will be discussing, okay? Right. So now just look at these questions. I will be showing you few questions. See, these are some questions based on chemical properties of haloalkanes, okay? So this alkyl bromide upon treating with alcoholic KOH giving A again treated with HBr. See, this kind of reactions they will be giving in the exams. This is also one of the chemical property question, okay? And this is also, see, inorganic an organic halide which does not undergo hydrolysis by SN1 mechanism. See, all of them are halides only now. So what we can conclude here? Yes, these are the chemical properties. The questions is based on chemical properties of haloalkanes, right? Whether you open JEE book, JEE previous year papers or NEET previous year paper or EAPCET previous year paper, there will be at least one question related to this chemical properties of haloalkanes, okay? It is particularly on SN1 and SN2 reactions like nucleophilic substitution reactions only, okay? So now just follow this session till the end so that you can get answer for any question related to these SN1 and SN2 reaction or particularly about the chemical properties of haloalkanes and haloarenes, whether it can be JEE, NEET or EAPCET exams. Yes, you need to understand this concept first, okay? Right, let us start our discussion on this. See, these are the things we discussed in the last class also, right? Okay, so now what are the chemical properties that haloalkanes will show? So here haloalkanes undergo mainly three types of reaction. What are those? Reactions with metals, okay? So haloalkane directly react with metal, we will see that, okay? And then next elimination reactions, it will undergo elimination reactions as well as nucleophilic substitution reactions. These are some three important chemical properties of haloalkanes, you remember. First of all, reactions with metal, it is very easy. See, you just take any haloalkane like methyl chloride I am taking. Yes, this is haloalkane, methyl halide, okay, or chloromethane right now. So this chloromethane upon treating with metals like magnesium mutate, okay. Now this reaction will be taking place in dry ether condition. What is the solvent used? Dry ether solvents to be used here, okay. So only dry ether, not wet conditions. If you use any wet condition here, any aqueous medium is present here, so magnesium react with this aqueous medium only, it will not react with this substrate, okay. So that's why we need to use this dry conditions here, okay. Now what happens? So this magnesium will be inserted between carbon and chlorine, so that you will get methyl magnesium chloride, okay, methyl magnesium chloride, okay. This is something like alkyl group is there and one halide is there right now. So you got alkyl magnesium halide, okay. This is something like RMGX, right? So this RMGX is called Grignard reagent. What is this? Grignard reagent. So Grignard reagent is one of the very useful organic reagent to be used in organic synthetic chemistry, okay. So now what is the use of this Grignard reagent? See here, Grignard reagent, what it will be giving us? See, always we know magnesium, it means alkaline earth metal, right? So metal means that should have a positive charge. How much charge? So it has 2 valence electrons that can be removed, so magnesium will be with +2. Okay, if this is +2, then carbon is more electronegative than magnesium, it's a non-metal, so it should be -1 and our halide ion should be -1. So here you can see our alkyl group like methyl group is having negative charge, okay. So a less electronegative atom having negative charge on it can act as a strong nucleophile. What I am saying? It's a strong nucleophile, or it can also show its basic nature also, okay. Now Grignard reagent can show its basic nature as well as nucleophilic nature depending upon the reaction here, okay. So between chloride ion and methyl carbene anion, okay, which is strong nucleophile. See, since carbon is less electronegative, it can easily donate its here negative charge electrons. So therefore I can say methyl carbene anion is more nucleophilic compared to the chloride ion. Therefore, whenever Grignard reagent is undergoing chemical reactions, okay, now Grignard reagent will donate, this alkyl anionic part is there na, like carbon anionic part is there na, so that will be the reactive site here, so that will be the nucleophilic site here, that will attacks at the electron deficient species. Okay, so now it can act as a good nucleophile and good base. Okay, let me show you some example. When you add Grignard reagent to water, like you can take RmGX, you are adding it to water, what happens, tell me? So water produces, it's a weak electrolyte now, so it will produces H plus and OH minus. See, our R minus, carbon with negative charge, OH minus with negative charge. So who will be more electronegative, carbon or oxygen? Oxygen more electronegative, no? Yes, you can place negative charge on oxygen when we have negative charge on carbon. So why, how it is possible? By donating this H plus ion to the carbon, it will give RH, that is alkane is formed, and you will get Mg, you have Cl, and here you will get OH. Okay, this kind of species is formed. So what you can remember, Grignard reagent upon hydrolysis forms alkenes. What it will forms? Respect to alkane is formed. Okay, whatever the alkyl group is there, alkyl group give respect to alkane. For example, here you have methyl magnesium bromide. So upon hydrolysis, what will be the product formed here? Methyl na, so you will get methane. If it is ethane, if it is ethyl, you are going to get ethane. If it is propyl, you are going to get propane. Hope the discussion is clear. So similar to this, when a Grignard reagent is treated with ammonia, what I am saying, it is treated with ammonia. So here also ammonia, generally we know ammonia is a base, like normally we will say this is a Lewis base, donates pair of electrons, like that, no? So now remember here, whenever you are treating this Grignard reagent, here carbon, which is a less electronegative atom than nitrogen, no? Therefore a less electronegative atom cannot hold a negative charge on it. So what it will do, it will abstract proton from here, and nitrogen now gains that negative charge. Okay, therefore you are going to get a methane. If it is methyl group, you are going to get a methane. If it is an alkyl group, you will get a alkane. So it is an alkyl group R, so you will get a respect to alkane like this. Okay, so if this is a CH3 minus, what will be the product formed? It will be methane like this. So this is a basic understanding you should have when you are asking about, or when you are studying about reactions of Grignard reagent with like water as well as ammonia things. Okay, is this clear? Whatever we are discussing, clear? So photon gaming in the chat box. Hello sir, hello my dear student here. Are you following the class or not? Just mention if you have any doubts during the discussion. Yes. Yes. Is there any doubt in the discussion? No, right? Yeah. Let's move forward. Yeah, this is about the reactions of haloalkanes with the metals. What is this? Reactions of haloalkanes with the metal. Okay. Then next here we have nucleophilic substitution reactions. One of the very important topic you need to be discussed here. Okay. So nucleophilic substitution means what? See, we are discussing about haloalkanes, right? So let us say methyl halide is there. Like this we have. Okay. So we know halide ions are more electronegative than carbon, right? So therefore, what happens during the reactions? What happens? Okay, so here carbon halogen bond will get polarized. How it will get polarized? Halide ion is more electronegative, so that will polarizes. That will drag the bonded electrons towards itself and generates partial negative charge on the halide ion and creates partial positive charge. That is electron deficiency on the carbon atom. Right now. So due to this reason, what happening? This bond getting weakens, and that is going along with this halide ion right now. So now halide, like halogen, whatever it is there, it will goes as a halide ion, like negative charge on it. So for example, if it is a methyl chloride, what you are going to get here? So your chloride ion is coming out along with these bonded electrons. See, it is going out as a negative charged species now. So now what is the charge present on the carbon? Positive charge, right? So now a positive charged carbon is there. So we can say this is an electron deficient site right now. So you can see here what I am adding, a nucleophile. What do we mean by a nucleophile? It is having tendency to attack on the nucleus, right? It means positively charged species. Why? Because nucleophiles are highly electron rich species. See, they have negative charge. So this negative charge now attacks at these positively charged carbons. Okay, right. Now what is happening? One negatively charged species is going out, again one more negatively charged species is coming in, or one electron rich species is going out and one electron rich species is coming in. So one group is substituted by another group now, and what type of groups there are? Nucleophilic groups now. So one nucleophile is substituted by another nucleophile. So that's why these reactions are called nucleophilic substitution reactions. Now what will be your product here? CH3NU. Okay, this Nu is nothing but some nucleophilic group. It's a generalized example. Okay, right. So what is the difference from here to here? Here to there. So one nucleophile is substituted by another nucleophile. Okay, now you need to know some basic terms. So the group which is going out from the substrate, see the starting material here we are taking now, that is called substrate. What you can call substrate. Okay, whatever the species attacking on the substrate is called a reagent. What you should call? It's a reagent. Okay, so now here our nucleophile is a reagent attacking on the carbon. So the group which is going out from the substrate is there now, that should be called as a leaving group. What you can call? Leaving group. Okay, these are the terms you need to know here, and this is our final product form. That's it. Hope the complete discussion is clear about the basic understanding of nucleophilic substitution. So nucleophilic substitution means what? One nucleophile is substituted by another nucleophile. That's it. Okay, is this clear or not, guys? Is this clear or not? First tell me in the chat box. If there is any confusion, please let me know. Yeah, if this is clear, just click on the like button so that I can confirm you are following the class. Okay, so now here you can see during our discussions sometimes like just now I told you carbon with a negative charge is there. Sir, you are saying that negative charged species can act as a proton or can act as or can attack on some electrophilic centers. Okay, so this negative charged species you are saying sometimes as a base, sometimes as a nucleophile. For example, OH minus is there. You are calling this as a nucleophile sometimes and you are calling it as a base sometimes. So when to say it is a base? Yes, so you can say a negatively charged species. A species is a base when it is attacking or when it is abstracting a proton. When it is attacking a proton or when it is accepting a proton, you should call it as a base. Okay, you should call it as a base. Okay, what you should call it as a base when it is attacking only on proton. Okay, if not proton, these negatively charged species are electron rich species attacking some electron deficient sites, like electron deficient sites other than proton, you can call it as a nucleophile. What you can call? Nucleophile. This is a very basic difference between basic nature and nucleophilic nature. Okay, this is a very fundamental difference between basic nature and nucleophilic nature. Okay, is this clear? Is this clear? What do we mean by basic nature and electrophilic nature? So you can say a species is basic when it is abstracting a proton readily. Okay, and you can say a species is more nucleophilic or nucleophilic when it is attacking an electron deficient sites like electrophiles. That's it. Okay, now we need to compare basic nature, that is basicity, and nucleophilicity when we are moving across a group like that. Okay, so for example, see chlorine, fluorine, all these are what? Chlorine, fluorine, chlorine, bromine, iodine belongs to a group right now, group 17 elements, right? So now what happens to this negatively charged fluoride, chloride, bromide and iodide species when we are discussing, when we are talking about their basic nature and nucleophilic nature? See, it depends on, basic nature depends on charge density. It depends on what? Charge density. So based on this, the like basic nature will be ordered in this way. So fluoride ion, stronger base, the next chloride ion, bromide ion, iodide ion. This is a basic nature. But when it comes to nucleophilic nature, that depends on solvation also. What it depends? It depends on solvation. So due to that reason, iodide ion is more nucleophilic than bromide ion, chloride ion, fluoride ion. So you can write in a group, in periodic table, nucleophilicity inversely proportional to nucleophilicity is directly proportional to size. Okay, in periodic table. Okay, and when it comes to basic nature, that is basicity is inversely proportional to size. These are the things to be remembered in periodic table. Okay, now when it comes to across the period, what I am saying, this is like when you are going from left to right in the period. Now what happens, both nucleophilicity and basicity, both of them are directly proportional to or you can say size, or you can say directly proportional to, like in the terms of electronegativity also you can give. So both, here I am writing, see, fluorine, chlorine, bromine, iodine we have right now, like this we have. So how do you give, which is more electronegative atom here? So fluorine now, so nucleophilic nature will be inversely proportional to electronegativity also they can give. Okay, so why I am giving these relations is, based on this relation you can expect a theoretical kind of questions. Okay, so now what you can say, nucleophilic nature inversely proportional to electronegativity, because electronegative species is at the bottom, so this will be more nucleophilic here. Okay, remember, so here nucleophilic nature and basicity, both of them are inversely proportional to electronegativity when you are talking in the periods. For example, I am saying here methyl carbene anion and NH2 minus and the next OH minus, I am giving this. Tell me which is more nucleophilic, they will ask. See, all of them are second period elements only, no? Now tell me which is more nucleophilic or more basic. See, a less electronegative atom can easily donate the negative charge on it to the electron deficient sites and even it for proton. Therefore, which is more nucleophilic or more basic here? Methyl carbene anion. Like this you need to write. That's it. This is the basic nature. Okay. See, oxygen is more electronegative. Therefore, it is less nucleophilic when we are talking or when we are comparing about within the period. Okay, within the period elements. That's it. Okay, is this clear or not? Is this clear or not? Now tell me between these two, the nucleophilic nature between OH minus and SH minus. So OH, where they belongs to oxygen, sulfur, like that, na? They are from the period, from the group, like down the group. Now down the group what happens, what I told you, down the group elements, see, for halides what you have seen, nucleophilic nature, down the group nucleophilic nature increases. So therefore SH minus is more nucleophilic nature, SH minus is more nucleophilic than OH minus. That's it. This is what you need to remember here. Okay, and guys, just try to remember here, nucleophilicity nature depends on solvent. See here, if it is polar protic solvent, this will be the scenario. Iodide ion, bromide ion, chloride ion, fluoride ion will be the basic nucleophilic nature. So if it is polar aprotic solvent, see I am using two words, polar protic, polar aprotic. So polar aprotic means there is free ions availability. So why free ions availability I will explain. Therefore it will be same as like a basic nature. Okay, so now in this case what is happening, sir? Nucleophilicity nature means here these ions get solvated. So due to that solvation, why solvation happens? Due to hydrogen bonding and all. So due to that reason fluoride ion is less nucleophilic because it will be get solvated more when we compare with the other ions. So iodide ion is more nucleophilic than bromide, chloride, fluoride. That's it. So this is in polar protic, this is polar aprotic. Try to remember the difference here. Okay, so now what are the different solvents we have? See, solvents can be classified as polar, non-polar, polar, non-polar. Again, polar solvents again classified into two types, protic solvents, aprotic solvents. Okay, so these non-polar compounds only that much. Okay, so non-polar means here most of the cases mu will be equals to 0, dipole moment will be equals to 0. Give some examples. See, CCl4 I am writing. Yes, in this case it's a non-polar, right? And the next benzene you can write. Solvent, na, benzene is also, and hexane. Organic solvents, most of the organic solvents here, hexane, heptane, next toluene, all this comes under examples of non-polar solvents. Okay, now what about this polar protic and polar aprotic? See, protic means they should have hydrogen bond donor sites, hydrogen bond donor sites should be there, donor sites. Okay, present, sites are present. Okay, and here no hydrogen bond, donor sites. Okay, let me explain with some examples. See here what I am writing, alcohol I am writing like ROH, alcohol is a polar protic solvent, whereas here I am writing DMSO, dimethyl sulfoxide, or you can take what is this? This is DMF. What do we mean by DMF? Dimethyl formamide. Dimethyl formamide is DMF. Okay, and the next DMSO I am saying now. So this is nothing but dimethyl sulfoxide. What is this? Dimethyl sulfoxide. So these are some examples you can say. Acetone is the best example for polar aprotic solvent. So you need to understand what is aprotic and protic, and it's a very important factor to be understood when you are talking about the chemical reactions like SN1 and SN2. See, first of all you need to know what do we mean by hydrogen bond donor. See, during hydrogen bond formation, see, there should be a hydrogen atom that must be attached to an electronegative atom. What? Hydrogen atom must be attached to electronegative atom. Okay, therefore hydrogen atom should get partial positive charge and electronegative atom will get partial negative charge, right? So now what happens due to these polarities, this polarized H plus ion will participate in some electrostatic interactions with the other opposite charged pole. For example, here I have water molecule. Now what happens? See, oxygen having lone pair now, so between these bonds also it will get polarized like partial negative charge on electronegative oxygen atom and positive charge on this hydrogen. Now what is happening, check here. See, the hydrogen atom is getting electrostatic force of attraction with this oxygen right now. So this electrostatic force of attraction between this hydrogen which is attached to more electronegative atom and between this oxygen, this is called hydrogen bond. What we can say? This is a hydrogen bond. So for this hydrogen bond formation, this group is providing H plus ion now. This group is providing, this species is providing hydrogen atom now. So you can say this group as this thing as hydrogen bond donor site. What is this? Hydrogen bond donor site. Whereas oxygen is accepting this hydrogen bond formation now. So you can say this is hydrogen bond acceptor. What you can say? Water molecule here, it can act as hydrogen bond acceptor. Okay, right. Now if you further understand that water molecule can form or can accept hydrogen bond using its lone pair electron with the other electronegative atom hydrogen, and here hydrogen that is present on the oxygen molecule also can form hydrogen bond with other molecules right now. So water molecule can accept hydrogen bond and can donate hydrogen bond. So therefore you can consider water molecule as the best example of hydrogen bond donor as well as hydrogen bond acceptor. Okay, so now by understanding this, just look at here. Oxygen can, water molecule can form how many hydrogen bonds? See, it can form hydrogen bond with these two hydrogens, okay, using other electronegative atoms. Therefore these are two donor sites of water molecule to form hydrogen bond donor sites. Okay, and using these two lone pairs of oxygen in the water molecule can accept hydrogen bond formations. Okay, therefore water molecule, one water molecule can form maximum of 4 hydrogen bonds. You can remember how many hydrogen bonds can be formed? Maximum of 4. Okay, 2 are by these hydrogen atoms and remaining 2 are by this lone pair electron, here one, here one. Like that 4 hydrogen bond formation can be possible by one water molecule. Remember this. Okay, so now those compounds which can capable of having hydrogen bond donor sites for hydrogen bond formation can be considered as polar protic solvent. What is this mean by polarity? See, these bonds are polar bonds or not? Yes, due to electronegativity difference, our carbons, these things will get negative charge. Less electronegative atom will get partial positive charges and electronegative atoms will get partial negative charge. So we can say these are polar bonds and hydrogen bond donor sites also there. So you can say polar protic solvents. Okay, and in this case there is, see what I am saying, DMF now, so dimethyl. So do we have here methyls? No. So if I write now methyls, what happens? See here, So this is CH3, CH3. Previously I have just placed hydrogen atoms. So using that hydrogen atom, now it can form hydrogen bond donor sites right now. So that cannot be a polar aprotic solvent, that can be polar protic. Now in the place of hydrogens I am replacing that with methyl groups. Now do we have any polarized hydrogen? No, there is no polar hydrogen bond to donate for hydrogen bond formation. So that's why this is a polar aprotic solvent. Okay, in this case also, do we have any hydrogen atom attached to electronegative atom? No, right? Therefore it cannot be a hydrogen bond donor site. It cannot be a hydrogen bond donor site, but it can act as a hydrogen bond donors from other species. So you can say this acetone is an example of hydrogen bond acceptor. What it is? Hydrogen bond acceptor, not a acceptor, not a donor. Okay, so what I am saying, aprotic solvent are those compounds, are those solvents which does not have hydrogen bond donor sites. Okay, so this is not having any hydrogen bond donor sites, therefore you can say this is a polar aprotic solvent. Which one it is? See, it's an acetone. See, these bonds are getting polarized. See, oxygen carbon bond, due to electronegativity difference, oxygen will get negative charge, carbon get positive charge. This is a polar bond, but it is not a protic solvent, that is an aprotic solvent. Hope the discussion of polar, protic and aprotic is clear without having any confusion. Guys, why I am repeatedly discussing this much times for this particular discussion is because you need to identify. See, during SN1 reaction, next we are going to discuss about SN1 reaction. I will be mentioning the solvent that favors SN1 reaction is polar protic solvent favors SN1 reaction. It means you will be having no confusion between SN1 and SN2 reactions once after completing that. So how can you able to identify that whether it is reaction following SN1 or SN2? Looking at its solvent we can have some clues, because if it is polar protic, that will favors SN1 reaction. If it is polar aprotic, then it will be favors SN2 reactions. Okay, so this is how it will be useful. That is what we can say solvent effect on chemical reactions. Okay, right. Let us discuss the chemical reactions, substitution reactions. Particularly I will be explaining here SN1 reaction. What do we mean by SN1 here? Unimolecular nucleophilic substitution reaction. Unimolecular nucleophilic substitution reactions. Okay, reactions. So now what happens in SN1 reactions? See, remember this, whatever the points I am writing, tertiary alkyl halides reacts faster compared to secondary and primary. Okay, right, this is what you need to remember here. Okay, rate of reaction depends on concentration of substrate only. Okay, it depends only on concentration of substrate, not on nucleophilic concentration. Okay, so in the rate equation, what are the things involved? Only substrate is involved. See, during a reaction there will be a substrate, there will be a reagent, forms a product, right? But rate of this SN1 reaction depends only on substrate concentration. Therefore it follows first order kinetics. What is a kinetics here? It's a first order kinetics. Okay, and in the rate determining step we are having only substrate involvement, no? So that's why we are saying it's a unimolecular, first order unimolecular. Okay, it means only one molecule is involved in the rate determining step. So unimolecular first order reaction. Okay, and the next one more thing is, see, if you have studied about kinetics, chemical kinetics, now they will ask you one question. See, what in SN1 reaction they will mention like this. In SN1 reaction, if concentration of substrate increased two times and rate and concentration of nucleophile also increased two times. How many times? Two times. Then what happens to rate of reaction? Then what happens to rate of reactions? It means rate of reactions how many times increases? That is what the question here making. Okay, so now what is the rate equation we have? Rate is directly proportional to concentration of substrate. Okay, and independent of nucleophile concentration, right? So whatever might be the scenario of nucleophile, whether its concentration increasing, decreasing, we don't care about that, because our rate is not depending on nucleophile concentration, it is depending only on substrate concentration. So it means rate, what happens, R1 equals to, I am writing proportionality as a K1, it's a constant, substrate concentration. This is first equation, let us say. Now how many times substrate concentration is increasing? 2 times, right? So it means K1, okay, here what happening to R1, let us say it is R2, so K into concentration of substrate increased 2 times now, to 2 times of concentration of substrate it is becoming. So now what happens here, so R2 is equals to 2 times K1 into substrate concentration. Let us write like this, yes, we can write it like this. So R2 is equals to, what happened, 2 into K1 substrate is nothing but R1, right? So R2 equals to R1. It means when we increase the concentration of substrate 2 times, rate also increased 2 times. How many times it is increased? 2 times. Okay, this is the fundamental way of understanding the concept of SN1 and SN2 reactions connecting to the chemical kinetics discussion. Okay, right. This is clear now? Right. Let us move little more further deeper here. See, if the substrate has chiral center, what is chiral center? If you don't know, I will explain, no worries. Chiral center, then chiral carbon halide bond that is involving the reaction, because we are studying about haloalkanes, no? That's why I am specifically mentioning, that is substrate has chiral carbon. It means that whatever the chiral carbon is there, that must involve in the reaction, then only this statement valid here. If the substrate has chiral carbon which is involving in the reaction, in SN1 reaction, will gives a racemic mixture product. What it will gives? Racemic mixture product. Okay, racemic mixture product. Or you can remember there is a question, so it will be 100% racemization or only partial racemization? Yes, it is a partial racemization. What happens in SN1 reaction? It is a partial racemization. Okay, this is a 2015 question. Okay, it will be partial racemization. Okay, remember this. Okay, it means what is this racemization and all? Just see here, for example, I am writing CH3 ethyl and this is some other alkyl group, let us say propyl I am writing, 2-propyl I am writing. So now here we have halide ion. Now what happens, tell me? So first of all this halide ion goes out. Okay, when it is going out, what is happening, just tell me? So it is going out first, so that you will get CH3 ET, so positive charge over here right now. So this is a carbocation. What type of carbocation formed here? So this is a carbocation which is a secondary or tertiary. See, this carbon surrounded by 3 other carbons, it means it's a tertiary carbocation. What is this? Tertiary carbocation. And this is intermediate during the reaction. What is the intermediate in SN1 reaction? Carbocation is an intermediate. Okay, so now rate of reaction depends on this intermediate carbocation formation step, RDS step, and this is what slowest step. Okay, slow step is considered to be rate determining step during a chemical reaction. Okay, so now what happens? See, this is an sp2 hybridized carbon. Now carbocation means carbocation hybridization is how much? sp2. If it is sp2, we have trigonal planar geometry. What is that? Trigonal planar. It means central carbon will be there like this and 3 groups will be like this and 1 empty p orbital will be in this manner. Okay, right. Now what is happening during the reaction? A nucleophile will come and attacks on this carbon. Nucleophile means negative charge species, come and attacks on this carbon like this right now. So either it can attack from the above the plane or it can attacks from the below the plane right now. So if it is attacking from above the plane, we will get one type of product. So let us write that kind of product. What is type of product here? See, let me write it in this way. CH3, see what I am writing here, just see. CH3 and here Nu. Okay, let us say our nucleophile is some OH group. What is our nucleophile? OH minus. So OH minus, if it is nucleophile, then you can write here OH group, like this OH you can write. Okay, and what is the one more type of product? See, if it is forming, this is a type A product formed when this nucleophile is attacking from above the plane. Now there is equal chances to this nucleophile to attack from below the plane also now, because it is a planar molecule. Like this you need to imagine like a plane. So OH can come from above the plane or it can come from below the plane. So if it is coming from below the plane, just see here what I am writing. ET. So OH is coming from below the plane. So this will be the scenario. This is B type of product. Now just understand what I have written there. So look at their configurations. What do we mean by configurations here? See, whenever a carbon having 4 different groups, see around the carbon there are 4 different groups. What are the 4 different groups? One is methyl, this is one type, and this is ethyl, different alkyl group, and propyl, different alkyl group, halide. 4 different alkyl groups are there now. So that carbon is considered to be chiral carbon. What I am saying, it's a chiral carbon. Okay. So now on this chiral carbon, see, let us say this is a halide ion. So if halide ion is present, there are 4 different halides groups are there. So you are saying it is a chiral carbon. So on every chiral carbons, there are something called configurations. So that configuration can be R or it can be S. Okay, that can be whether it is R or S can be decided based on the priority groups. What do we mean by priority groups? Just give numbering based on their atomic numbers. If atomic numbers are same, look at their mass number. Okay, like that. So based on that you need to give the priorities. For example, here I am writing priority. Just tell me what is happening here. See, our OH group is oxygen, more atomic number than carbon, carbon, carbon. So this is 1. Okay, and this is a carbon. Here ethyl also carbon, but here propyl also carbon, but propyl contains more number of carbons. Now here 3 carbons are there, so this should be prioritized 2. Then ethyl 2 carbons are there, here methyl only 1, so this should be 2, 3 and this should be 4. Like this you need to consider the group priority. So this is called CIP rules. What is that? Kohn-Ingold-Prelog rules. So what is the use of that rules? To give RS nomenclature. Okay, that configuration we are going to give here. So now tell me here, so OH is 1 here, and the next this is 2, this is 3, this is 4. Okay, so now the least priority group here, if you see least and high priority groups, see here high priority group is above the plane, the least priority group is below the plane. So least priority group should be below the plane, and if this rotation, see priority groups how they are arranged. See, I am changing the color. See how they are arranged: 1, 2, 2, 1, 2, 2, 2, 2, 3, 3, 2, 4. How they are arranged? It is a clockwise, no? Yes, clockwise, and least priority group is below the plane. So if it is clockwise with the least priority group below the plane, you should call it as R configuration product. What you should call? R configuration product. But here if you observe, our least priority group is not on below the plane, it is above the plane. So if this is a clockwise direction, you should not say it as R, you should say it as S. Why you are saying it as S? Because least priority group is at above the plane, no? So configuration becomes opposite. See, least 4th priority group below the plane, clockwise direction, you should call it as R. Anti-clockwise direction, priority groups are in anti-clockwise, S. Okay, so this least priority is on below the plane, fine, it is accepting this, and clockwise direction. So yes, you should call it as R configuration. And look at this, least priority group is above the plane and this is clockwise. It means it will not follow the statement, so configuration becomes opposite. So clockwise becomes S here. Okay, hope the discussion is clear. Guys, this is one of the very important topic whether you are preparing for NEET, JEE, EAPCET. I am mixing completely here to explain you the content. Okay, so now what is the intermediate during the process? It's a carbocation intermediate in SN1 reaction. And now what type of solvent favors this reaction? So solvent favors here is polar protic solvent. What is that solvent? Polar protic. What is the best example for polar protic? Like water, aqueous medium, water. Okay, and alcohol also polar protic. Okay, these things which has proton donor site, hydrogen bond donor sites, you can say polar protic solvents, that's it. Okay, so this is about the discussion of SN1 reaction, right. Let me give you some examples here. So which of the following involves or readily involves in SN1 reaction? See, I am writing here bromine, chlorine, fluorine. So which of these readily involves in SN1 reaction? A, B, C. So it depends on what now? See, substrate alkyl groups are same, but here halide bromide, here chloride, here fluoride. So it depends on halide ions now. So the halide ion which leaves easily from here can involve faster now, because that will forms carbocation readily and that will proceeds further. Okay, so it means which halide ion will comes out first? See, always remember fluorine, chlorine, bromine, iodine. Now what happens to the size down the group? Size increases now, iodide ion is bigger size. See, fluorine is very small size, like carbon also belongs to the fluorine period only now, like 2p series, second period, right. So due to this same group same period elements, their sizes are almost equal, okay, our sizes are almost same. So due to that reason, that overlapping, bond overlapping will be very strong in case of carbon and fluorine. So due to that strong bond strength, the bond breaking of that bond will take more time, so it will be less reactive, like carbon fluorine, it means this is least reactive in the given three compounds. So which is more reactive? Down the group size increases, bond breaks easily, therefore bromide ion is a good leaving group compared to the chloride and fluoride, and iodide ion is very better group, better leaving group when I compare with all these things. So what is the reactivity order? So A is more reactive than B, is more reactive than C, and if I add one more compound like this, iodide, where it comes? Yes, iodide is larger size now, so it will be first here. So D will be first. So more reactive is D, next A, B, C. Okay, hope the discussion is clear. Guys, if the discussion is clear, just click on the like button and you can share with your friends who are preparing for this exam. Okay, right. Right, let me take some water. By the time you just try to answer me this question, otherwise. See, now I am changing a slight. Yes. So in this ABC, which is more reactive in SN1 reaction? Tell me. Which is more reactive in these three compounds in SN1 reaction? Those who are watching the live session can answer me, which is more reactive here. See what I told you, formation of carbocation is intermediate here, and that will be the rate determining step. So where the carbocation formation is easier, see if you remove this bromide ion, you are going to get a tertiary carbocation like this, right. So in the GOC we have studied the carbocation stability order. So if I remove bromide from here, so what happens? You are going to get a secondary carbocation in this manner. So here if you remove bromide, you are going to get a primary carbocation like this, right. So which is more stable carbocation here? Tertiary, right. So formation of tertiary carbocation is easy because the respect to carbocation is stabilized by more number of alpha hydrogens. See how many alpha hydrogens are there? 3, 3, 3. 9 alpha hydrogens are there. 9 hyperconjugations can be possible here. Okay, so due to that 9 hyperconjugative forms, A will be more readily reactive because respect to carbocation formed is easier, and that will shows chemical reaction faster. Okay, so what is the rate of SN1 reaction for these three things? A, B, C, that's it. This will be the scenario. Okay, right. Okay, is this clear or not? Whatever we discussed, clear, right? Next, I will give few more questions. Yes, tell me, out of this A, B, C, which compound is more reactive in SN1 reaction? Reactivity in SN1 reaction, tell me, which is more reactive? So how do you answer this one again? So based on stability of carbocation, in which case carbocation is more stable, tell me. See, if you remove these chloride ions, try to remove, just assume that, imagine that you are removing these chloride ions, then we will get a positive charges on these carbons, right, like this. So all these carbons, if you observe, they are benzylic carbons. What they are? They are benzylic carbons. Okay. So now that benzyl carbocation stabilized by mesomeric effect of pi electrons from this ring. Okay. And along with that, what type of groups here they attached? Here, if you see methyl group is an electron releasing group. Our carbocation also required a group which releases electrons into or towards that carbocation side, right now. So if this group is releasing electrons towards carbocation side, then it will be more stabilized. Whereas here we have electron withdrawing group, right now nitro group is electron withdrawing group. Now what happens? This nitro group only withdraws electrons from the ring towards itself. Therefore what happens to our electron deficient carbon? It will further destabilizes. Why? Because already this carbocation is electron deficient. Again it is not having electrons already. Okay, less electrons are present here. Again this fellow is dragging, this electron withdrawing is dragging electrons towards itself. So it makes this carbocation very less stable compared with the other case. So therefore C will be least reactive because the formed carbocation is the least stable, that's why. Okay, and between these two, here electron releasing group is there, that will stabilizes the formed carbocation effectively. So it means B will be more reactive because respect to carbocation stability is more due to the presence of electron releasing group at the para position, and there is no such group. Yes, this will be in intermediate between B and C, like this you can write BAC will be your answer for the question. Okay, is this clear guys, those who are watching the live? Right, now I will be giving you few more questions, just tell me your answers for these. See guys what I am writing. Between this A and B, which is more reactive towards substitution reactions itself? I am not even saying SN1, SN2, directly saying, yeah, even in SN1 or even in SN2, order will be same for these both compounds. What is the reactivity order? Tell me. See, you might be thinking, sir, it is a tertiary carbon. If I remove this chloride ion, we will get a tertiary carbocation like this. So this is a tertiary carbocation and this is a secondary carbocation. We know secondary carbocations are less stable than tertiary. It means this will be more reactive, you might be considering, but no. Okay, so remember these are called non-classical carbocations. What I am saying, these are called non-classical carbocations. So these cannot be stabilized, this carbocation at this bridgehead. So this is called a bridgehead. Okay, so here it cannot be stabilized by any of these effects. Okay, so therefore these carbocations cannot be formed first. Okay, so this group will not comes out, it will be an inert site you can say. Okay, only the second one will undergo substitution reaction, not this first one. So only second will be reacting, not the first one. Just remember this, whenever we have a bridgehead carbocation, that will be highly unstable. Okay, therefore only the normal, the side groups will be undergoing chemical reactions. Okay, right, this is what you need to remember here. Okay, right, next one. See what I am adding here to this AgNO3, what I am adding to the AgNO3, I am adding NaCl. What happens here? We know it will form AgCl. So it will form AgCl precipitate and NaNO3. NaNO3 will be formed. See, AgCl precipitate is formed. In the similar way, when we are treating the compounds, for example, here I will be taking one compound here. Just see. So they will ask whether this will form precipitate with AgNO3 or not, whether the given substrate forms precipitate with AgNO3 or not. For example, I will be giving you few other compounds here. Let me take like this, they will give. So they will say this is option A, option B. So which of the following compound will form precipitate with AgNO, silver nitrate solution upon treating the given substrates with silver nitrate solution, which will give white precipitate or which will give precipitate. First of all, why they are forming precipitate? See, they are forming precipitate due to formation of AgCl. So this is a white precipitate. Okay. So due to formation of AgCl, you will get a white precipitate. Yes, that kind of precipitate is possible in this case or not, or in this case or not. This is the question. See, for the formation, what we have removed here, we removed it as a chloride ion, right now, Na plus Cl minus. So here also remove it as a chloride ion. What is the resulting species we will be getting here? We will get a 5-membered ring with a positive charge on the carbon, right? So this is a compound. Just observe this compound, whether it is aromatic, non-aromatic, anti-aromatic. What is the scenario here? Positive charge. See, 4 pi electrons only it has. Cyclic compound having conjugation. See, pi bond, sigma bond, pi vacant orbital. Again sigma bond, vacant pi bond, like this. So it has complete conjugation, cyclic compound. 4n pi electrons are there, 4 pi electrons are there. It means it is an anti-aromatic compound right now. So if this is an anti-aromatic compound, it is highly unstable. What I am saying, this is highly unstable. So if it is highly unstable, so this is highly unstable now, therefore this kind of highly unstable species will not form, okay, because it will be less stable, it will undergo decomposition. It means first of all this equilibrium will not favors forward, okay. So this reaction is not possible. It means AgNO3 precipitate is not absorbed in the first reaction. Let us study about second reaction. Now try to remove this chloride ion with the help of AgNO3, so that we will get a carbocation like this, okay, and we will get AgCl precipitate here. So now what is the scenario of this this carbocation formed here? See, cyclopropyl carbocation, here we have propionyl carbocation we have. So tell me what happens. Yes, pi bond, sigma bond, positive charge. Yes, that is in complete conjugation like this, right? And how many pi electrons are there? 2 pi electrons are there. We know there is a rule called Huckel rule. 4n plus 2 pi electrons should be there in the aromatic compound. Aromatic compound should be a cyclic one, should be have a planarity in all the carbons, and like this planar compound, and complete conjugation of pi electrons should takes place, and with a 4n pi electrons, 4n plus 2 pi electrons. So n value put 0. Okay, so how many pi electrons we have? Yes, 2 pi electrons, right? So here 2 pi electrons are there now, right? I can say this is an aromatic compound now. So since it is an aromatic compound, it is highly stable. Okay, aromatic compounds are highly stable because their all pi electrons lies in lower energy bonding molecular orbitals, right? So due to that reason these are stable, so it can be formed. Okay, so out of this A and B, which is forming precipitate with AgNO3, only the cyclopropyl halide will be forming, propionyl halide will be forming, but not the first case. Okay, that's it. Okay, so you need to choose only second one will form precipitate but not the first one. Like this they will make 4 options. Okay, which are the following gives precipitate with AgNO3. Okay, it's easy, right, identifying that, right? Okay, right. See, mostly whenever you are studying about reactions, before coming to the reactions, you should be very strong at GOC part. okay, like electromeric, like electronic effects are there now, inductive, mesomeric, hyperconjugation, and along with that you need to be clear with this aromaticity concept, that's it. Okay, if you are clear with this, right, most of your reactions and reaction mechanism part is very easy and smoother. Okay, you can learn it very easily. Okay, right, let me show you some questions. After that the remaining part will be discussed in the next session, that is tomorrow's session. Just tell me here, yeah, so look at this, ease of ionization, ionization to produce carbocation and bromide ion under treatment with Ag plus, that is nothing but AgNO3 solution only they are saying. Easy, in which case they are asking, in which case AgCl, AgBr precipitate, AgBr yellow color precipitate, light pale yellow color precipitate will be formed easily, in which case they are asking. If the formed product, formed carbocation by removal of these bromide ions, if it is stable, then we will get the precipitate formation easily, right. So in this case I just now told you, if you remove this, get a positive charge, this is an anti-aromatic compound, it won't precipitate. Okay, if you remove this, yes, here positive charge, pi bond, lone pair, this say aromatic, yes, this will be giving you the precipitate easily. See, never ever remove bromide ion directly attached to the like benzene ring, because if you remove this, the benzene ring or phenyl ring get a positive charge, right, that is highly unstable. So never ever remove this, so it will also not get precipitated. And what about here? Yes, it can precipitate, I mean it can comes out and formation of positive charge is taking place there, that is allylic carbocation, but it is not aromatic. Okay, so here we have a resonance effect for stabilization, and here we have a aromatic nature. So which is more predominant here? So due to the aromatic nature, more conjugations are there here, and it is all pi electrons in lower energy states, so it is more stable now. So this compound will be easily ionized. So your option 2 will be the perfect answer for the question. Okay, right, let me give you few more questions, you can solve them, and answers for them will be discussed in the upcoming sessions, I mean in the next session. This is one question. Okay, right, this is discussed. This is the second question. Okay, just look into them. This is SN1 reaction. Yes, today's discussion only, you need to solve this. This is a NEET question, right? This is also SN1 reaction. Yes, you need to answer this question also. Two questions, one is from NEET, another one is from JEE I given. Again, this is also number of moles of AgCl formed in the following reaction. Again, same whatever we discussed, based on that you can follow SN1, SN2 reactions. I mean you can just use the SN1 concept also to get the answer for this. I just want your answer for these three questions by the next class. Okay, the remaining topics will be discussed in the upcoming sessions. Stay connected with our NEET World channel, and if you have any concerns or any doubts, please write in the chat box. Feel free to ask your concerns or mention your concerns. Okay, yes guys, if you like these sessions, share with your friends who are preparing for JEE, NEET or EAPCET exams. Thank you.